We're going to talk about critical thinking about statistical inference, and that's important. And you need to bring everything to bear that you've learned in the previous semester, previous block. But let's start with a little side note. What has always baffled me, even when I was a young kid, and I even felt excluded out of stuff that other people were doing. I grew up on a elementary school which had a Catholic inclination, and I wasn't raised in any Catholic way. My parents were atheists, or are atheists, and they raised me that way. And it always baffled me. So other children would come to school and they got a new watch or a chain or whatever, and they did their first communion, right? So I thought I wanted that too, right? So give me that ritual. I want to partake in that ritual so I can get the goodies, right? And give me the gifts that you would get from other relatives. One of the rituals in the Catholic Church is that you I don't even know the exact name of it, but that was one of the things that baffled me when I was in the church for the first time, that everyone would stand up at a given time and walk to the front and get this not particularly nice tasting piece of symbolic bread and eat it and drink some wine. I thought that was weird, and I thought it was weird as well when everyone said peace to each other and shook each other's hands, right? So these are all examples of rituals, right? So that things that people do because people before them did them as well, which once started with a good idea in mind, right? So there's some shared idea of community for sure when you shake each other's hand and say peace be with you. But that might not be the direct reason that people are currently doing it when they attend a mass in church. Perhaps the most pressing reason why they're doing it is because other people are doing it and because everyone before them did it as well. It has become a ritual. And there are weirder examples of rituals to think of. So this example from quoted by Marewski and Olsen about a village in Bavaria where people at the beginning of the 19th century believed that if man slept badly, that could be attributed to the Trud, some type of ghost, and you could do all types of weird things to counter the influence of that ghost. And another example of a ritual closer to home would be what we're teaching you as a university department. Another ritualistic way of acting, which has its origin in some original good ideas. So people had good intentions and proper, tools in mind for solving actual practical problems, but it has resulted in a mindless way of doing stuff because other people are doing it, rejecting null hypotheses because the p-value is smaller than an alpha of 0.05. So perhaps what you've learned so far, I hope not, because of course Sharon's lectures about it are excellent, as are Johnny's in the first year. But what we want to avoid in training you as a scientist practitioner is that you become ritualistic in testing your hypotheses, that you become ritualistic in how you use statistics for trying to find out what you're interested in. I want you to become more mindful in how you use statistics and more mindful in how you test hypotheses, and perhaps even invite you to think of alternative ways of testing hypotheses. So that's what we're going to talk about today. We're going to see that statistical significance that you've been so focused on all this time might not explain everything, as the koala bear is surprised by here in this meme. And we're going to make sure that you properly understand what you're doing and what you can and can't conclude on the basis of null hypothesis significance testing. Then we're going to have a look at common thinking errors, fallacies, if you will, related to that type of statistical reasoning. And in the end, we're going to talk about an alternative way of doing statistics. And it would be a short introduction to Bayesian statistics, which Sharon will build on in the next lecture next week, and which will finally culminate in the debate that we'll have at the end of the block between Erik-Jan Wagemakers and Denny Borsboom. So last week we talked about the publication process as it should be ideally, and how it is actually in actuality. So what we ideally people would review publications on merit and not just on whether a significant p-value was produced by the research. But that's actually what people do grade the paper on. So the same paper was graded in a more positive light, reviewed in a more positive light, if it yielded significant results compared to when it didn't yield significant results. A couple of people in the comments are saying that the view is blurry. If it is, just grab the slides from Canvas and read along there to make sure you can read everything. I don't know what the problem is, but I'm gonna move on for now and hope things will be resolved for your connection issues soon, or my connection issues indeed. Okay, so we're overly focused on whether a p-value can be considered significant or not. Basically, what we're saying is, yes, if I have a significant result, I can publish my studies, right? Whatever I was thinking and predicting turned out to be right, or was probably right. Power is no longer an issue. Forget how many participants I used or what effect size I expected, because here it is. It's an effect, right? I've proved that an effect exists, and I've proved that my research is replicable. I mean, it's a bit blunt the way I'm summarizing things, but basically that's what we're focused on, right? It should be significant, because if it's significant, I'm basically right. But then, given the same decision procedure, a problem results if it turns out to be that that p-value isn't below the actual alpha threshold. And what should you do then, right? So it all works out fine if your decision procedure, rejecting the null hypothesis if the p-value is lower than the alpha level, that works out fine if indeed that p-value turns out to be lower than the alpha level. If it isn't, what should you then do, right? I can't reject the null hypothesis, so then what? What should I write down? Should I just go to the corner and cry about it? Or could I perhaps somehow try and inform my readers about the fact that, well, it wasn't significant, it wasn't below that threshold, but it was really, really close. Is that informative or not? And weirdly enough, it isn't informative. It doesn't matter whether that p-value was actually very close to the threshold or not. Or it matters depending on what perspective you take on null hypothesis significance testing, because there's actually different ways that you can go about it, following the Fisherian approach to statistics or the Neyman Pearson approach. We'll get back to that. But for now, researchers are, well, confused by the fact that, well, if I can't reject a null hypothesis, what can I do? Is there something interesting in my data anyway that I can inform the readers about? So they start building on that and reasoning about that. And, well, you should help them out, the researchers. So my question to you is, let's say, how can we actually interpret, give a precise interpretation to the fact that the p-value is lower than the alpha level, right? So what does the comparison between p and alpha actually yield in terms of useful information and conclusion? Is it 1, you have absolutely disproved the null hypothesis, 2, you have found the probability of the null hypothesis being true, 3, you have absolutely proved your experimental hypothesis, 4, you can deduce the probability of the experimental hypothesis being true. 5, you know if you decide to reject the null hypothesis, the probability that you are making the wrong decision. Or 6, you have a reliable experimental finding in the sense that if, hypothetically, the experiment were repeated a great number of times, you would obtain a significant result on 1 minus alpha % of occasions. Whew, so that's a mouthful. Or none of the above. That's option 7, not listed here. Is it none of the options listed above? So what is the correct interpretation here? Is it 1, 2, 3, 4, 5, 6, or 7, none of the above, or any combinations of these? I'm getting a 2, a 7, a 6, a 5. I want you to really think about it, whether you post a number in the comments or not. Consider for yourself what interpretations you've considered to be true in the past.
Can I give an explanation why I choose 5?
Sure, go ahead.
I think it's 5 because the alpha level is the type 1 error.
Mm-hmm.
So if you decide to reject null hypothesis, the probability that you are making the wrong decision. So you have a 0.05, so like 5% chance that you reject the null hypothesis even though it's actually true. Right?
if that indeed
Right.
is the case. So given that the
Yeah.
null hypothesis is true, the probability that you rejected an error is 0.05%. So 5 isn't correct because you're making the assumption that if you decide to reject the null hypothesis, the only possibility is that the null is in fact true. But there are two options, right? The null is either true or it is not, and we don't know which one is the case. We only know if it is true, then the probability of rejecting it anyway is
Oh yeah, I
0.05%,
didn't read it correctly, I
right?
think then.
No,
Yeah,
but
yeah.
don't feel bad about it because the whole point of listing all these alternatives is that a lot of people make these mistakes. So if you would list these 6 options, basically out of undergraduate students, everyone would at least choose one of these 6 options and endorse it as correct, even though they are all incorrect. All 6 options are incorrect. But it gets a bit worse because not only undergraduate students, but also actual researchers and professors teaching statistics make these type of mistakes. Not to the same extent, perhaps, as undergraduate students, but still at similar levels. I mean, you could critique this type of research, right? You could say, well, it's misleading that the option 7 that I did indeed point out wasn't included in the original research. Because usually you ask a multiple choice question in which at least one of the answers is correct. But it does show that people are not that clear as we should perhaps be in our thinking about interpreting the comparison between P and alpha. So very good, and thanks for your input and your reasoning on choosing option 5. And it's the most tricky one. So if you look at the research, I think if people choose one of these options, it's most likely that they choose 5 as being correct. So that's the one that confuses most people, perhaps because of its phrasing. And after this lecture, it should be clear to you why all 6 interpretations are, in fact, incorrect. All right, so to get to a proper sense of what it does mean, the comparison between P and alpha, we have to go back to the basics. And I'll try to keep that short, but we're going to grab some tools from our critical thinking toolkit that we started using in the first block. We need to realize that statements in which alpha, power, and p-values occur relate to frequentist or objective probabilities. And statements in which those entities occur relate to conditional probabilities. So that's 2 aspects that we need to properly understand or ingest. We need to properly understand what we're talking about: objective conditional probabilities. So what does that mean? I'm basically summarizing stuff that we did talk about in the first block when we talked about critical thinking, but it's worthwhile summarizing that a bit. So if I'm saying, let's say I wonder whether Sharon has visited Australia somewhere in his life, and I say, well, it's improbable. To me, it's highly improbable that Sharon has visited Australia. What I try to say then is my subjective probability, or the subjective probability that I give to the statement Sharon has visited a certain country, isn't very high. So my degree of belief that the statement is true, that Sharon has gone to Australia, is very low. That's what we mean with subjective probability, the degree to which we are convinced that something is the case in the world. Objective probability, hence the name, isn't about our conviction about something being the case, but it's about the degree to which something actually is the case. So the basic difference between subjective and objective is actually, objective, we're talking about the state of the world, right? So if I draw a card from a deck of cards, or if I roll a fair die, or if I toss a fair coin, in such and such percentage of cases, that result will occur. That's just a fact about the way the world works, right? We're talking about a proportion or a long-run relative frequency, which is a common interpretation of objective probability. So to give you another example, if I toss this coin infinitely often, 50% of those infinite amount of tosses had will be on top. So that's about what will be the case in the world. If we toss fair coins infinitely often, 50% of them will be on top, and that reflects that objective probability of 50% chance of either outcome. If you try to predict the weather and you take all the measurements that you can currently have on one specific day, and on the basis of that you run a lot of simulations, and if it turns out that in 50% of those simulations of what the weather will be like tomorrow, it turns out to be raining, then you can say that there's a 50% probability of rain tomorrow, because in 50% of slight variations on the measurements you took today, it actually turns out to be raining. So it relates to the state of the world. And in the same way, you need to think about p-values and alpha. So that's what that convoluted definition actually means. So if there's no difference in the population, this t-value or more extreme t-values do not occur very often given this specific procedure, right? So if you would infinitely repeat this procedure and there were no true effect in the population, then it's highly unlikely that this t-value would occur. And that means that you won't encounter that t-value a lot of the times if you were to infinitely repeat that specific procedure. Right, so that should be clear that we're talking about objective probability when we talk about p-values. Same way we talk about objective probabilities when we talk about alpha. Right, if you decide to reject or null, given that p-value is lower than 0.05, given that the null hypothesis is true, I will make an error in 5% of cases. That means that if you repeat that same procedure an infinite amount of time, and the null is true, then you will be wrong in rejecting the null in 5% of cases. Objective probabilities, long-term relative frequencies. That's the type of probability we talk about when we talk about p-value. And that also already gives you a part of the answer, right? That gives you part of the answer why some of these interpretations are wrong. Because if you consider that a p-value reflects a conditional, an objective probability, then it's weird to say that the probability of the null hypothesis being true is such and such. Because if you're talking about objective probability, that means that you're talking about the state of the world. And the state of the world, in terms of hypotheses being true, is black and white, right? The null hypothesis is either true or not. There's no degree to it. There's not an infinite range of hypotheses that are sometimes correct and sometimes not correct, right? So it's weird to talk about the probability of the null being true or the alternative hypothesis being true on the basis of objective probabilities. Because objective probabilities are about long-term relative frequency, and it's hard to come up with a correct interpretation of a long-term relative frequency for the null hypothesis. It's either true or not. So what people probably do when they reason about the null hypothesis probably being true or not is that they switch from that objective probability to a subjective probability. They're not actually saying that there's a long-term relative frequency of the null and in such percent of cases it turns out to be true. No, they switch when they say the fourth statement, for example, here, or the second statement listed here. They switch to that subjective definition of probability. And they say the degree to which I'm convinced that the null is true or the alternative is true is such and such. So what people are doing in making these mistaken interpretations is confusing subjective and objective probabilities. That's the first ingredient. The second one has to do with conditional probabilities, and this part you're more familiar with, right? What it means to talk about conditional probabilities, you should get that hunch, right? We talked about a specific hunch that you should get as soon as people start inversing conditional probabilities. It has to do with this fantastic movie, or it's a sequence of movie even, because I think they're at the 7th or the 6th installment now. But let's use a different example than we did using Sharknado 1, because in Sharknado 3 something slightly different happens, because the sharks end up being in space, and the humans as well, and they still eat each other there. So let's say somebody asks you, given that you've died, right? You end up at the gates of heaven, and Peter asks you, well, you're dead. I'm sorry. What are the odds that you died being eaten by a flying shark in space? You would agree with me that the probability is very low, right? Given that you died, that being the cause of death, that probability is fairly low. But if then this happens, again, this is without the audio, I'm sorry, but it's a short fragment. All right, this again is Ian Ziering explaining to us why you can't inverse conditional probabilities. Because if this has happened and somebody were to ask you, you've just been eaten by a floating shark in space, what is the probability that you'll die? You would say, well, I think it's fairly likely that I'll die given that I've just been eaten by a flying shark in space. So again, you can just go around inverting conditional probabilities. The probabilities that given that you've died, the probability that you've been eaten by a flying shark in space is fairly low. But the inverse of that would give at least a much higher probability, right? Given that you've just been eaten by a flying shark in space, the probability that you'll die is somewhat higher. Again, the Sharknado hunch. It should apply to your statistical reasoning as well. I can't just go around inverting conditional probabilities. Okay. As Boromir says here as well in the meme, one does not simply inverse conditional probabilities. So understanding that a p-value in alpha and beta reflect conditional probabilities should trigger that Sharknado hunch, right? Should trigger that sense that, wow, what I've just been given by my statistical package is the p-value. So that says something about probability of getting at least this test statistics, given that the null is true. And I can't just go around inversing those two terms and saying that they reflect the same number, right? Then you're inversing conditional probabilities, and you can't just do that because you're likely to make an error then. All right, so we've looked at, or we try to regurgitate, two aspects of p-values and alpha, right? So one, they're objective probabilities, and two, they're conditional probabilities. And you should be familiar with what that means and how it relates to these different interpretations. So what goes wrong here is that people are confusing objective and subjective probabilities, and or they are inversing conditional probabilities, which you cannot do. The question that might then remain, if we're not allowed to conclude all this, what can we conclude on the basis of the p-value and perhaps a comparison between p and alpha? And there are actually two good answers to that, but they offer different perspective of the usefulness of this whole procedure. First of all, the man who thought about p-value in the first place, who invented it, if you will, at least in its more modern use, was Ronald Fisher. And Ronald Fisher, he was delegated, if you will, to a agricultural station in the UK, and he had the assignment from his employer to figure out which type of fertilizer worked better on a given patch of land. And what he wanted to do was control for all the factors that might affect how well a patch of land was doing in agriculture, besides just the type of fertilizer that was used. And up until that point, random assignment to conditions was not something that people had thought about. And that's what something he thought up and applied to that agricultural research. And he made different plots of land. You can see here different squares of land. And he just randomized the process of allocation of fertilizer or something else to those different patches, which allowed him to quantify something. It allowed him to quantify that if the only thing that produces the difference that I observe between different patches of land, so the only thing that produces differences in the samples I'm taking here, is actually pure randomness, so random allocation to the fertilizer or the non-fertilizer condition, then I can quantify how likely the difference in results would be. So we found difference in result between different patches. So the land turned out to be very fertile or not so much. And his question then is, well, if the only thing taking place here is the result of my random assignment, how likely is then this result or more extreme? And what Fisher thought was, I'm here basically in the outback thinking about statistics, and I think this is a useful tool. So he wrote it down in a manual. I think it was called significance testing for statistical workers. So in doing so, he made this procedure accessible. He made it accessible to other researchers to reason along the same lines, to say that, well, I can at least, it's difficult to say, to filter out all the different alternative interpretations that I can apply to explaining why I found a difference, but I can at least quantify this one. I can at least quantify how likely would this result be if there's actually no difference in the population by using this p-value. And he said, well, yeah, you can do this as following. So formulate the null hypothesis, which, by the way, doesn't necessarily mean that you're using the actual null value of no difference, no predicted difference in the between the conditions. It just said he called it the null hypothesis because that's the hypothesis you're trying to reject, right? So it's the hypothesis you're trying to nullify. That's where the term originates. And you report the exact level of significance, precise p-value, and you don't discuss what you should be doing about accepting or rejecting hypotheses. So this was Fisher's approach. You just give the reader of your research a p-value, and you leave it up to the reader to interpret its value. And at best, what you offer the reader is something that we talked about last week, right? You're playing the devil's advocate. You're saying, well, if there were no actual difference, how likely would this type of result or more extreme actually be? That's the type of information you give the reader. And that's of limited value, right? That you can consider that as the first step, which is what Fisher considered it to be. What he said was, well, use this type of procedure only if you know nothing about the subject matter. What you're basically doing is trying to give an argument for, well, it would be unlikely that I found these results if nothing were the case, right? As a first step in trying to further study the phenomenon. And Fisher also said that you should only accept a certain conclusion if your research, if you repeat it a lot of times, rarely fails to give a significant result. So he also thought about using the p-value as one step in a sequence of repeating the same research, right? So he only saw the usefulness of that p-value as a first step, and only if you would do the research multiple times, and the research will rarely fail to show a significant effect. But perhaps that's somewhat limited, right? Perhaps you want to do more, and you get the sense that something is missing, which is what competing scientists back in the day, in Ronald Fisher's time, thought about this as well. What they wanted to come up with is using that p-value, but using it for something else. You're using the p-value not necessarily to play the devil's advocate. What you're using it for is as a heuristic, if you will, in your decision scheme. So you're basically setting up two hypotheses, the null and the, we've ended up calling the null and the alternative. They called it hypothesis 1 and 2. And you should critically think about the beta level and the alpha level for your test and do a proper power analysis, which means that you use this procedure only if you can make a clear cost-benefit analysis. So making type 1 error or type 2 error, what are the downsides to that? And in what way do I favor making one type of error over another type of error? And if you can't make that cost-benefit analysis, then this type of reasoning would be not that useful. So what they came up with was a way of performing inductive behavior and not really reasoning about what conclusion is probably true, because that would require those subjective probabilities we've been talking about. No, they were reasoning about what behavior would be justified in what case. So given you set your alpha and your beta levels in a specific way, you're justified in rejecting the null in certain cases, which would mean that you behave in a way that won't result in an error in a lot of times, given that you set the proper alpha and beta levels in a substantive way. So you're actually not concluding that the null hypothesis is true or false. You're behaving as if it were, right? It's similar to saying I've got a production line in industry somewhere. I'm producing light bulbs, and you got to test, right? You take a sample out of the batch of light bulbs that's produced, and you check whether those are functioning well or not. And for that type of decision, you can set your alpha and beta levels in a proper way, right? Because there's an actual cost to producing type 1 errors and type 2 errors. People returning the items because they're not working well, or your procedure being so strict that the cost of production increases. And then it makes sense. You're not concluding that all light bulbs are correct. No, you're acting as if you're producing proper light bulbs. And sometimes you might be wrong because the customers will return their items. And in that context, it makes sense, right? Reasoning about light bulbs and production and type 1 and type 2 errors. And you could start to wonder whether we should apply the same type of inductive behavior to testing hypotheses. So this was a somewhat detailed account of two different perspectives on what we can actually do with p-value. One person, Ronald Fisher, said, well, give it to your reader and your reader can use it as an indication or to use it to play devil's advocate, right? So if there were no effect, how likely would this effect or more extreme be? You don't compare it with alpha levels. You don't do a power analysis. You just give that p-value and leave it up to the reader. Neyman and Pearson had a different perspective, and they said, well, you don't really need to publish the exact p-value. What you only need to do as a researcher is compare it to your alpha level and only check whether it's below or above that alpha level and act accordingly, which is a completely different perspective. And these gentlemen didn't agree with each other. Things got so bad that they, which has a lot to do with the history as well. I spare you the details, but it had something to do with Ronald Fisher. He couldn't get along with the dad of one of the guys depicted here, and that's one of the reasons that he ended up in that agricultural station, which he didn't like, where he thought of the p-value. So they very much disliked each other's approaches to doing statistics. And that's one of the important points here, is that there's a lot of people, statisticians, that disagree with each other. And that goes a long way to explaining all the stuff that you encounter in SPSS, right? So perhaps you've wondered, as I do, as everyone does, why is there a box that I need to check or uncheck or not for this specific value? And if you ask around or check in Google, then sometimes the answer is, it doesn't really matter, or... Right? So there's a lot of stuff in SPSS that you don't actually need, or you don't need, or somebody else has decided for you that you don't need. Why is that the case? It's not really efficient. No, that's because there's a lot of statisticians that make things up as they go along, and they disagree with each other. And if you bundle all the stuff they've came up with in the past 100 years, then this is the statistical package that you get. That reflects the disagreement and proper debate in the field. So basically, we started out with a p-value, playing the devil's advocate, and we've plugged that into that decision procedure from Neyman and Pearson, and that's the stuff you're more familiar with, right? So given that we do a bunch of tests, we assume that in some of the cases there will be a real effect, and in some of the cases there won't be a real effect, and then we can set our error rates using the power and the alpha levels to make sure that if there is no real effect, we won't make a lot of errors. And if there is a real effect, we also won't make a lot of errors as well. And those are the sensitivity and specificity that we used in those frequency trees last week. Apply to your, last block, apply to your reasoning about power and alpha as well, which I've tried to make explicit here. And if you want to play around with those sensitivity and specificity settings and see what it does with your type 1, type 2 or error rates, you can also visit the specific page in which you can move around these distributions. All right, so the result is that we've ended up with a blend of these two perspectives. So we've looked at what does a p-value actually mean, so long-term, so objective conditional probabilities, and we've looked at what can we actually do with them. Well, there's two approaches. Either use it to play the devil's advocate and saying, well, if there were nothing going on, this would be highly unlikely, or this were more extreme, then this would be highly unlikely. Or you can use it for a decision procedure, which you should only use if your theory makes for proper prediction, right? So that's the only way setting the power or the beta levels in the proper ways. You know what type of effect you can expect if your theory holds. We've applied it in a situation in which researchers, on the one hand, don't repeat their research very often. You often look for significant effect and publish that and don't repeat research because replications tended to not get published over the past years. So even though Fisher said use this only or you can only conclude anything about the null being true or not if an experiment rarely fails to show significant result, right? That's a sequence of events, so we need that sequence of event. That's something that we ignored. On the other hand, we have Neyman Pearson, which said, yeah, you have to have a proper cost-benefit analysis, which is also not something that we're doing, right? We're just following the leader and we're saying, well, the ritual is to set alpha at 0.05 and set beta at 0.80, or just ignore power altogether. And that's what we ended up doing. It's like an illicit love child of these gentlemen, right? We've blended the precise p-value with the alpha and the beta level, and both sides of the debates would disagree with what we're currently doing, which you can call the null ritual. Set up a statistical null hypothesis of no mean difference or zero correlation. Don't specify the predictions of your research hypothesis or of any alternative substantive hypotheses. Use 5% as a convention for alpha, and if it's significant, accept your research hypothesis, and always perform this procedure. So this shows dogmatism or a ritualistic approach to hypothesis testing, which both sides of this debate wouldn't actually agree on. So what we've seen so far is that p-values alpha and beta level reflect objective conditional probabilities, and you know what that means for the way in which we can interpret them. And we've seen at what actually was the original proposal of what we should do with p-values in alpha and beta, which are the differing perspectives of Ronald Fisher and Neyman and Pearson on the other hand. And we've seen that we've ended up blending these two approaches into something that cannot be considered a very thoughtful approach to doing statistics. All right, go ahead.
Just the question is, if Fisher doesn't use an A level,
right?
How does he determine if his p-value is significant or not?
Well, he wouldn't call it, so that it's a subtle difference. So let's see. It's basically, he did write down the 0.05 criterion, right? So in his manual for statistical workers, he did note the 0.05 and the 0.01 criterion for saying, well, if your p-value is up and about there, then you can say you've perhaps something significant is going on in the traditional sense, right? Where it's not to be expected in noise. So he said, well, if it's up and about here, you could consider it significant. But he didn't say this was an alpha level that is part of a form of inductive behavior that would mean that you're not actually concluding that the null is true or not, but you're just behaving like it is or not, which would result in one type of error or another type of error in the long run in such and such percent of cases. As I said, we've ended up with a blend of the two approaches. And it's weird looking back at these, well, historical perspectives, if you will, because if we look at just the Fisherian approach, we would say something is missing, right? Missing the alpha level and correcting for multiple comparisons, etc., etc. And if we just look at the Neyman-Pearson approach, something is missing as well, right? Because we teach you to report specific p-values, and Neyman-Pearson, they would say it's not relevant because you're not concluding anything about the null being true. No, you're acting in a specific way, which would yield in an error so many percent of the cases. So the only thing that's relevant in the long run is that criterion of 5%, not your precise p-value in one specific experiment.